Now let's look at some applications. We're going to talk about angle of elevation and angle of depression in a given situation. And maybe you've heard of these things here. They say a lot of stuff here. There's a lot of stuff. So let's go down to here. Angle of elevation. Okay? So angle of elevation is, like, you see this diagram over here? We got this guy sitting on an island, he's looking up at a plane, right? His line of sight goes up by that angle, right? It's called the angle of elevation when it goes up like that, okay? We're good with that. So if you hear angle of elevation, that's the angle you're talking about. And this picture could be switched to the other side too, right? So it doesn't really matter. Now, there's another type of angle, and we got to be real careful with this other type of angle. Angle of depression, okay? So the angle of elevation going up, the angle of depression would be doing what? Going down. From where is the thing, right? So, if you take a look here, you see this airplane? Its line of sight to the guy on the island is this angle up here. But you see this? You need that horizon line, okay? Because if you don't have that, you don't have the angle of depression, right? So it needs a horizon to be an angle of depression, okay? So for example, here's a mistake, right? You see the car? This would be, right here, would be what angle? Angle of elevation. Is this the angle of depression right here, this angle 1? No, why not? What does it not have? It would need this. That would be the angle of depression. You see the distinction there? Okay? That's not the angle of depression. That is. You need that horizon line. Everybody get that, right? So don't make that mistake. Angle of elevation down here, angle of depression with a horizon line up there. Everybody with me? Okay? All right, let's go to some examples. And there's some examples that they love on the readings, man, there's tons of them. They always got some kind of ladder leaning against the wall, right? They love ladders leaning against walls. Now, one thing we can always assume, okay? When they give you a word problem and has some kind of structure, like a wall or a tree or a guy standing somewhere or a building, whatever, you can always assume, they won't tell you, but you can always assume that that structure is perpendicular to the ground, okay? So we can always assume, unless they tell you otherwise, structure, whatever it is perpendicular to the ground. And that's important because what kind of triangle will that give you in the situation?
Right.
A right triangle, okay? And now, the other thing that we can assume is that anything that's like a string or a wire is perfectly straight, okay? We know it's not. Everybody ever see, like look at telephone poles. See the wires, are they perfectly straight from one pole to the other? No, they sag down a little bit, right? That's actually called a quaternary curve. It's not a parabola. You've heard of parabola. It's not that, right? Parabola is close, okay? But in these problems, we tend to disregard any curving of a wire that's hanging. We assume it's pulled taut and effectively straight, right? So assume also all wires, strings, etc. are straight, not curved. And that'll give you like a nice hypotenuse for your triangle, right? Okay. So here's a ladder problem, right? So if we look at this here, like here's the foot of the ladder, the base of the wall, right? That'd be the distance from the foot of the ladder to the base of the wall. This angle 1 would be, what would we call that angle there? That angle 1. Angle of what?
Elevation.
Elevation. Is angle 2 the angle of depression?
No.
No, it's not.
Right.
It would have to be the horizon up top there, right? Here's one that they'll kind of disregard every now and then. So they got some, some guy flying a kite here. So first of all, kite string, we can assume it's straight for the purpose of the problem, right? But the triangle for this, like if you want to find the kite string, wouldn't it be like here? Okay, right? Assume it's straight down from the kite. So a lot of times what you'll have, and sometimes they'll disregard this, is he's standing on the ground, right? So like, maybe they'll ask you to find the height of the kite, right? Well, you could use this right triangle and get this distance right to here. But to get the true height of the kite, what would you have to know?
To the ground though.
Right, you'd have to know like how far above the ground is his hand holding it. Okay? Sometimes, for simplicity's sake, they'll give you a diagram like this, which I guess you have to assume he's holding the kite string with his toes. Right? But for simplicity's sake, you might see something like that. But a lot of times, you know, they'll tell you, okay, he's holding the kite 3 feet off the ground. So you'll find this, right? And to get the kite's height, whatever you find that to be, what do? Add 3 to it, yeah.
The length of the string is wrong because it goes behind.
All right, yeah. So, you know, the length of it probably from his hand to the kite. The useful string, the string that's doing the work, is starting at his
I
hand.
mean, it didn't specify the useful string. It specified the string.
Well, we got to make that an assumption, yes. Okay? Well, you're going to have what's coiled up on the thing too, the other 500 feet coiled up?
Yes.
Yeah.
Okay, let's not do that. Okay. Here's one where you got a sapling, a tree, got to be held up by a wire. That's called, anybody know what that's called? It's called a
Guy
guy wire, right? You guys ever set up a tent and you put those wires that go out? That's called a guy wire, right? I don't know why. Maybe it's like the equivalent, like you could have a guy standing there holding it, or if you can't find a guy to hold the tent all weekend, you could get a wire. I guess you call it guy wire. I don't know. Okay? But I mean, look at the tree, right? But what can we assume?
It's a right track.
That it's perpendicular to the ground, okay? Unless they tell you otherwise. Huh? I just told you we can assume that, okay? We can always assume that in these problems unless they tell you differently. You'll see problems like this where the sun is coming behind this guy and he's casting a shadow. So the shadow would be that part of your triangle. What would this part of the triangle be? The sun's what? Rays? Okay, something like that. And this will be the height of the guy. Well, they even had it right there. What are we doing?
I'm not
This will
sure.
be, oh, we got lunch coming. Okay. Let's flip over to the next page. Let's get our lunches quietly. So here's one like we saw on the first page, right? Viewing something in the air like an airplane, or viewing a kite or bird. Okay? Hang on for a minute here. So I guess it's to reiterate, right? Now, with a problem like this, let's say they want to know how far is it from the plane to the guy sitting here on the island, right? We could use the angle of depression, and we need that horizontal horizon, right? Okay? Would it also be an equivalent triangle if we had, let me just do it in red maybe, that there and use the angle of elevation? Would that be the same triangle dimensions? Because don't we have a rectangle here, which is a parallelogram, right? And what could you say about these two guys? What did I just mark them as? Parallel, and these, right, are parallel. And also, since it's a rectangle, the opposite sides are what? Congruent, right? And so that's congruent to itself. So wouldn't the triangles be congruent by side, side, side? So you could use either triangle you like to get the same measurements, right? Like, if they gave the angle of elevation or angle of depression, right, and you do this out, could you very easily find the angle of elevation? What would these two angles be? And therefore congruent, right? Because it's a parallel rectangle. You see what I'm getting at? So we've got to think about the other stuff we did. Because there might be a different way to get it across. Somebody might draw it this way to get at it. Someone might draw it that way. Okay? But they both work. All right, let's look at some problems then. So, first one here, we got a tree being held up by that guy wire. What do they want to know?
What data is
What is the angle formed between the wire and the ground? We call this angle what?
data?
Angle of elevation right? They didn't say it, but that is the angle of elevation. So we got a right triangle, don't we? So if we want to find that angle, and we got a couple of sides, we're probably going to be using trig, right? We just learned some sine, cosine, tangent stuff. So what trig function are we going to use? What's this? Opposite, and this is what? Hypotenuse.
Sine.
The wire. Yeah, so your equation is sine of theta equals 3 over 3.4. How do you get at theta? What do you do to both sides? Take the inverse, what? Sine. Yeah, you don't want to take the inverse cosine because you want to get rid of sine, right? So you know how to do these, right? So once you get this set up, it's the same as the ones we've been doing. So the setup is oftentimes drawing the right diagram with the right triangle, okay? So here's another one. I guess it's a ladder, right? 15-foot ladder. So that's what part of this diagram? The 15 feet is what? The hypotenuse. Against the wall, 52 degrees. That's our angle of elevation, right? How far from the wall is the ladder? So that's this distance here. We have a right triangle. Remember, assume perpendicular, right? So to find this distance x, what the trig function we're going to use? Because this is adjacent, right? So cosine of 52 equals x over 50. We've done a million of those, right? You multiply both sides by 15, push buttons, okay? Now over here, it's one with the sun casting the shadow from the pine tree, right? They want to know what's the height to the nearest meter. And they spelled it the British way. Okay. Yeah. Angle of elevation, height of the tree. So this is what to the angle? Opposite. And this is what? What trig function? Tangent. And we've done, now once you get there, it's the same as what we've been doing. You get the idea? Okay, so now we're just going to, it's really going to be the same problems. It's just now you have to draw your own diagram. Let's look on the next page. All right, now we got this. So this is good. This is bad. Whatever. What's wrong? Does anybody ever fly a kite with a toe? See what I mean? I'd rather have them holding it 3 feet off the ground and get done just add 3 to get to how high the kite is, whatever, right? That makes sense? But they want to know the length of this kite string. Okay? To the nearest what?
What?
But always pay attention to that. Don't do stupid Regis points, okay? Well, this is adjacent. This is hypotenuse. Cosine. Oh, this is one with the x in the bottom, so what can we do?
Switch them.
Right. That x equals 4 over cosine 37, push buttons, okay? So what I want you guys to do right now is read this first one, A. Draw a sketch it. Listen, here's the thing. Sometimes they'll tell you it's a tree or a house or something, and I go around and look at your sketches, and you got like a house with windows and some idiot looking out the window or a tree, and you're putting all the leaves in. Just draw the right triangle, man. You got all day for this. Just draw the right triangle, okay? All right, take a minute and see if we can set up A. We don't need a fancy sketch. Ladder, window 8 feet up from the ground. I'm just going to draw that wall, right? Here's my ladder. Simple enough, right? That's all I need. That's my ladder.
Oh.
So it's 8 feet up from the ground. That's 8 feet, okay? 10-foot ladder. Where does the 10 go? That's the ladder. And you want the angle formed between the ladder and the wall. Is that this angle? No, that's the ladder and the ground angle. It's this angle, right? So I'll put my theta in there. If you want to use an x. Okay. So what's my equation to solve this? Cosine theta equals, there you go. Everybody got that? Adjacent over hypotenuse. What do I do now? Take the inverse cosine of both sides. So this gives us theta, and they sent around to the nearest whole degree, right? Came out to what, actually? Well, what did it come out to?
36.86.
36.8, whatever, so that's 37 degrees. Everybody good with that one? Okay. Let's take a shot at the second one then. Draw a simple sketch. So it might look like this. About like that. So, or maybe you got it flipped over this way. That doesn't matter, right? Okay. So it'll be by your setup, right? Okay. Anybody want to give me the equation we're going to use?
Sine. 48.
48 degrees equals
H.
h over 50. It's pretty easy to solve, isn't it? What do we do to both sides? Yeah. Well, I mean, we know that. Can we just shortcut the next step? If we multiply both sides by 50, won't we end up with this? Right? I think we're all at the level now we can assume what we did here, right? If you saw that, you knew we multiplied both sides by 50. We don't have to show the little baby step anymore. Just like the new steps, right? The new stuff. Like inverse, take an inverse cosine, stuff like that, right? So what's the height of the kite?
37.
Round to the nearest what? So 37. I'll put approximately feet. All right, one more here. Read that one over. Draw a picture. Darn it. Forgot to hit record, but here's the setup. Angle depression. So we're solving for that x. So what function? Go ahead. Okay, so give me the equation. Tangent. Yeah. I got a stupid thing going on here. So tangent of 15 degrees equals 3,000 over x. You know how to solve that, right? What's our next line look like?
Yes.
So what's the next line?
X equals 3,000.
Over tangent of 15. There we go. So what do you get? Careful. See this? You see that?
21.96.
Well, round it correctly.
I got 11.
1,000.
Nearest 100 foot.
1,000.
11,200, isn't it? To the nearest. And that makes sense, right? Because, like, if you're really doing this, do you need, like, to the exact foot versus it really going to make a difference in a practical situation, right? So that makes sense. The nearest 100 feet, right? 1,200. Okay. Let's see if we can hit a couple of Regents questions. I guess we'll have to finish it tomorrow. What's your time doing? So that's what we'll do. We'll hit a few of these Regents questions here. I'm not going to get through them all. And then we come in tomorrow, we'll finish the rest of them. We'll do a review. Maybe we'll do 5-5 and then review the tests. We'll see. I got to make up my mind. Well, there's questions about it on there, right? I mean, cool. I'll make it a bonus. I don't know. I'd rather be able to teach it to you, right? Let's look over the first Regents question here. And it's nice they gave us a diagram. Are we? Well, yeah. Okay. I guess the fourth question is where are we going to put the variable? We're going to put it where they want to know something and where? What do they want to know?
The height.
So where do they put the variable? Down here? That's the height? Yeah, this guy right there. Put an X there. Now write an equation and solve it. Let's see. Trayton, you got an equation for us? Okay. We'll take a look at it. At least tell us which trig function we're going to use for the equation. There's our angle. What's that side? What's all the way over here? That's adjacent next to it. What's this side?
So,
To that angle.
I don't know.
Well, it's either opposite, adjacent, or hypotenuse. What's this side to that angle? Okay, and what's this where they gave you a number? Hypotenuse. Opposite hypotenuse. What's the trig function? Don't tell them.
Yes.
No, so what is it? Who keeps whispering his answers? Are you doing that? What is it?
I'm sure.
Sine. Yeah. Wait, were you going to try and say it? I was trying to extract it from him, though. So, yeah.
I get it.
Okay. I'll find someone else to extract from in a minute. Mackenzie, what's our equation? You know we're using sine. I'm extracting. You know we're using sine. Huh? Okay, but what's the actual equation? There we go. Sine 32 degrees equals, say it again. There you go. 129.5. So you're going to do what to both sides? Yeah. That'll give us this, won't it? Right? We know what we did there, don't we? I mean, you can show that stuff if you want. What we got? Hmm? 68 point what?
One.
Feet. Choice one. Are we good with that? Okay? So it depends on what they give you, whether you pick sine, cosine, or tangent. Okay? Let's move on to number 2. Yolanda, springboard. Nearest 10th. Sure. Ashlyn, which trig function are we going to use?
Wait, what?
Ashlyn.
Oh, I was confused.
No.
Hi, Ashlyn.
Sine. There we go. Erica, what's our equation? There we go. Solve it.
Stanford.
Take it. What's the next line?
Times.
What? X is in the bottom. What can we do? You ever heard me say that? Switching? You never heard me say that, did you? That's amazing. I'm amazed right now. So it's what? 65. How about I just do this? Over what? This becomes 8 over what? There's no 16.5 in this problem. What is there? It's not 16.5. What is it? Sine of 16.5. That's not equal to 16.5. Right? What we got? 28.2 inches, right? Okay. So we can squeeze another one in here. You're going to want to draw a picture here, guys, just like the one we did in the notes. Draw a rough sketch. Oh, this is tricky.
1/2 miles.
So, the free has started here.
What's half a mile?
Okay, hang on. Here's something you really need to know. And this would be a conversion they put on the reference sheet on the actual readings. But, yes, say that one more time. Because, listen, they're giving you a length of a mile, and they want to know the answer in what? Feet. So you need to know how many feet are in a mile. You said it? 5,280 feet in a mile. Everyone knows that, right?
That's
And, well, you know it now, right? Don't ever forget that.
2,600 degrees.
5,280 feet in 1 mile, right? So if I say 1 mile equals 5,280 feet, but this is half a mile. So what's half a mile equal?
2,640.
5 feet or something.
Now we can draw and label a diagram that's useful. Does that make sense? How many feet in a mile, everybody? 5,280. Okay? So now you can draw a picture. Bless you.
Bless you.
Bless you.
Bless you.
Not like
Angle of elevation. So this is 11.87 degrees there, right? One point of the ground. Base from my man. So what's the 2640? What part of the triangle?
The bait.
Hmm?
The
Bottom. Yeah. Okay. So this is 2,640 feet. 6. And where do we put our variable?
That's right.
Over here. I like to use a variable that makes sense, right? H for height. Yeah. Okay. I'll go ahead and set up an equation and fix this because that's unreadable. Oh, let's see. For a shut, what trig function are we going to use? Tangent. Evan, what's our equation? Equals H. What'd you say? I thought you said H. Over. There you go. Now it's just like all of them, right? Good. Multiply both sides by 2640, but you know that'll end up being this. Right? Ms. Pfeiffer, what's your answer? So you got 554.89 probably?
great job.
Can't make it. So it's 555, okay?